Right, so we're going to have a short little video just to finish this section where we'll be looking at the directional derivative along a curve. So let's just remember what we do normally when we differentiate. If we have a function of x, so if we're going along in the x direction, and we have a function traced out somewhere here, given by y is that a function of x, then it's what you're calculating when you differentiate y is the rate of change of y in the direction x. Okay, so f dashed of x0 is the rate of change of f in the direction of x. So what happens when we differentiate along the curve, which is the x-axis? Now we want to generalize that, and maybe the best way to sort of visualize this is to go back to my motivational river example, and imagine that you're going down this river in some curve. One thing that you might want to know, and this is where my drawing is going to get really dodgy, but let's see what we've got. I'll sort of try and make a riverbed or something along the bottom of this, and perhaps it changes or whatever, various points. Well, one thing that you can do then is associate to each point on your curve here, as you're flowing down the river, a depth function, a depth value, because you'll have it defined for the entirety of the river, and we're going somewhere in the river. And then what you might want to know is, as I travel along the curve, how fast is it getting deeper or shallower? Okay, so if, let's say this is, we've got d here, so this value d, which is a function of the point P, so a function of xy. So if we want to know how fast, let's call that P, how fast the river is getting deeper, at point P on the curve, then we want the directional derivative of the function d, which I've written as f, so this is the depth function along the curve. Which will be given by usually a gamma t. So it's worth just pointing out that depth here is a zero form, and that's what we're going to be integrating. Now, a zero form is literally just at each point of your affine space, or some subset of it, it's just going to be some quantity. And in this case, the depth we can view as just a quantity. So that's what it is we're going to be able to differentiate along the curve. So let's have the definition, and this is 2.46, directional derivative along a curve. So we let C in AM be a curve with parameterization gamma, and f some function that's defined on AN, and it just gives us some quantity at each point. So let f defined on AN going to Rn, to R, be a 0 form. And so that could be depth, for example, if you're in that river situation. Then the directional derivative of f along gamma is just going to be defined, well, notated in the following way: d sub gamma dashed of f equals d dt of f of gamma of t. Okay. So gamma is tracing out a curve, so it's giving you points with coordinates, and then we can feed them into f, and then we can see how quickly that's changing as the point moves along. Right, so let's recall that gamma dash could be considered as a vector field on C. So if you've got your curve and you're taking any kind of if you've got your curve and you're